My name is Kresten, and I'm CTO in this company called Humio. And I'm going to talk about log analytics and why we do it, how it works, some examples, and it's a bit of a squeezed schedule, so hopefully we'll make it all the way through. So just really quickly, what I'm going to talk about, a bit about what Humio is, how it works, and some stuff about how I ended up here. And actually, I'll just start a few minutes about how did I end up here. So, so this is me. That's my profile picture, Kresten. I am a language compiler, runtime geek. I spent the beginning of my career in Silicon Valley doing Objective-C, compiler, runtime system, core libraries, and I've spent a bunch of years working professionally on GCC and Java virtual machines. And I'm really kind of, the two things I really, I'm really interested in are on the metal performance, how to make things run really fast, and then also kind of understanding complex systems. And those are the two interesting aspects of programming languages from my point of view. You know, they need to run fast, of course, but they also need to express something that makes it easy to say what you want to do, easy to understand other people's programs, etc., etc. So this kind of understanding and describing complex systems has always been a core kind of interest for me. And I'd say when I worked in Silicon Valley in a real product company at Next Computer, I really, learned to appreciate this leverage that exists in doing product development. So product development really is the sort of drug that I get high on, because you build something and the more people use it, there's really leverage in that. Then after that, I moved back to Denmark, and I've been living in Denmark since '97. I spent 20 years at Trifork, kind of building up that business, building up our conference business at Trifork. So this is mostly a services, a consulting business, and over my 20 years there, we built all kinds of complex, bespoke software systems with all these, increasingly distributed complex systems with, been all the way through application servers, enterprise service buses, starting with cloud and microservices and all kinds of distributed systems, DevOps. And today it's really more clear than ever that no system is an island. They're all connected. And when you're building a system, it consists of multiple services, not just the services you build, but typically also other services or services you depend on to build it. And it's just become increasingly complex to just even understand these systems. And so one of the last projects I worked on at Trifork was this centralized healthcare infrastructure for the Danish Drug Administration. And there we really learned the value of centralized logging as a tool to understand complex distributed systems. Nowadays, all large enterprises do it, but I still meet people who don't do centralized logging, and it's almost like not doing unit testing to me. It's really something that everybody should do, because it just brings so much value. So when you look at it today, we're sitting developing systems at in our tranquil work environment or home office or wherever, and the stuff we're working on is far, far away. So we have these complex systems that are far away. We can't really see them. When I was a newcomer in software business, the computer was something that was sitting right there in front of you. It was like a workstation or a personal computer. But nowadays, that's really far away. So how do we deal with complex systems and understanding and monitoring complex systems that are far away? Now, other engineers have worked on this problem, and this is a picture of one of the lunar missions in the Apollo project, and you see the distinct characteristics here. They have some overview pictures on the wall there, and then if there's something that's amiss, something that's weird, then you can go and ask one of these people down there for details or digging in, doing kind of an incident response or whatever you want to call it. And I think these two kind of modes of operandi, kind of overview of high-level live data and then kind of digging into the details, are really valuable ways of thinking about it. So today, this is called observability. And in the mainstream tech media, you need metrics, traces, and logs, and that's like the recipe for making this successful. But often you see people using different tools, right? They have one tool for metrics, another tool for traces, another for logs, and while they have nice custom UI for that particular use case, they're often not really properly connected. And I think the common ground for all these really is interactive log analytics. That's our experience, is that with look at everything as logs and let these different use cases, and there'll be other use cases than just metric, traces, and logs, other angles on this data. It's really all about something that has a timestamp and there's some information associated with it, and you want to display it in various forms. So we set out to build a business that does this, has this point of view, and kind of our holy grail was some of the problems we looked at, and we realized as we were building this, first complex system, big complex system in our experience, the healthcare project. We really want to record everything. It's annoying if you have, license limitations and constantly hitting the roof, because often when you have a problem, it's something you didn't think of beforehand, and you want to go back and kind of have the full context, the high fidelity data. Then you want something that makes it super easy and convenient to have this interactive search on large data sets. So I'm thinking of it as the way you play with data in Excel. In an Excel spreadsheet, you can put some data in, you can write some formula, resort columns, and just kind of interactively work with the data in that same kind of playful manner. Or the way, if you're searching at Google, you just type some keywords and maybe some ands and ors and pluses, etc., and just have snappy responses and interactive. Working with large data sets doesn't necessarily mean that it has to take a lot of time. So then we have had really good experience with generating metrics and alerts from logs in real time. So data is arriving, and if there's something interesting, we can generate triggers or metrics out of it as the data is arriving. And we set out to build a product that was easy to install, also on premises, because kind of we came from a background of healthcare and financials, and at least 6 years ago when we started Humio, these businesses were not really eager to go into SaaS and cloud deployment. That has kind of shifted, but we still have a lot of business in this area as well. And finally, you want it to be affordable, of course, in terms of hardware, license, operations, easy to run, etc. So that's really the mission we're on. We want to take this is so valuable for understanding complex systems that everybody should be doing it. It's like, this is, getting back to the parallel to unit testing. Before people started unit testing or doing JUnit or continuous testing, it wasn't really obvious what the value was. But if you're not using centralized logging, then I guarantee you when you start using it, you'll realize that this has enormous value for understanding your systems. So the concept is really simple. It's Humio is this piece of software that can take all kinds of event logs from diverse systems of different kinds, and it really boils down to these two use cases: the metrics/monitoring use case, where you react and show live data, and then kind of a more incident response mode of operandi. That's the guy sitting there in front of all the screens and on the lunar mission picture from before. Log search, drill down, kind of technical business intelligence, you could call it. And so we built the first version of this. And actually, one of the first customers we got was a healthcare organization that wanted to use it for security. So we were thinking, the context was all DevOps, but it turns out security has a lot of data, and they have actually been, just like the DevOps world and centralized logging, the security world are doing a lot of the same things in a range of different security products. And there's endpoint security, network security, all kinds of aspects of security are dealt with by doing log analytics as well. So the first customer 4 or 5 years ago that was really big was like 1 million events a second, 20 terabyte of data a day. And so they were pushing like all the Windows logs from 30,000 desktop PCs and network traffic monitoring events. And then we're doing this exactly for those same two use cases. So it's really nice to be able to mix and match the data. So you can search for an IP address, you can search for a username, you can search for a particular kind of service across all these things. And then, we spent, the first real year to prove the tech, building scale-out clustering, and then in 2008 we got the Bloomberg as an enterprise customer. So we built out these features for enterprisey things. Last year we spent going cloud native, so we re-architected to work really well in virtualized environments, now we're really working to scale the business. So we've really been enjoying working with some of our lead customers. So almost every year there's been like a lead customer that has more or less driven the next year's worth of development, and that has worked really well to have everybody in engineering engaged. So for instance, 18 was the year of integrating with Bloomberg, doing advanced authentication profiles that would integrate with Active Directory, and so they could define access rules and various management features and failover scenarios, etc., for a large enterprise. 19 was the year where we built out the infrastructure to run really well on in cloud environments. So initially we built it actually to run really well on dedicated hardware in your own data center, or you've been running it on like physically rented computers. So that's an interesting journey. So now we have, on the good side, of 150 customers, paying customers that are actually using it. Some of them big, some are small, and both in DevOps space and security space. So let's see what it looks like. I thought I would just give like a 5-minute demo here before we move on. Let's see if I can find my mouse here. I'll share this window. So this is what the core UI. There's admin and organization around it, but the core UI is basically like a search panel like this. So here I have some sample data that's a honeypot we've set up, which is an SSH daemon exposed on the internet that you can, so we just get the syslog output from there. So there's lots of logs like this that indicate that you can search for the regex. Somebody's trying to hack our system. They're trying to log in when there's a port 22 open somewhere, so I can use a regex like this to search for all the failed login attempts. And so I can drive data out of this. I can say the IP address is actually this part. So this just gives a name to that part of the match. So if you look at one of these log lines, it now has an IP attribute. So we can use this to say, show me the top IP addresses, for instance. So say over the last 24 hours, we've had attacks from these, so we can search further back and say, the last 30 days. It's going to take a little while longer to go back through that data. So that's the core part of it. You can drive data out of it, and this stuff like this can be visualized. So you can put this up. A pie chart is probably not a good illustration of the attackers. But then you can take these visualizations like this and put them on a dashboard. And I have a little dashboard here that could contain, like, this is the same as I showed before. Show time charts of various kinds here. I have which cities are they trying to attack from, etc. So this part of the visuals here is something you could put on a dashboard on a wall, and you can drive alerts, basically triggers of levels of these values, and send events, call webhooks or emails or whatever. And you can drill down into the data as I showed you here on the center. So I'll jump back to the presentation. So now you have like a basic idea of what Humio looks like. We only have 20 minutes more. So the next little section is on how does this work? And then I have some examples of kind of things we learned along the way towards the end. And really the kind of the core interesting thing is you don't want to waste hardware. I think this quote by Henry Petrosky, it was Martin Thompson who kind of popularized this. The most amazing achievement of the computer software industry is its continuing cancellation of the steady and staggering gains made by the computer hardware industry. So hardware is getting better and better, but what do software people do? We waste it away because the cost in software world is man hours and time to market. So it doesn't really pay off to do your engineering well, except if you're in a product business. And you want your customers to save money and be able to do volume, then it makes a lot of sense. So kind of course, the gold standard for Humio is how we stack up against the competition in terms of how much hardware you need to throw at it to do like equal performance. So it's some of our main competitors. We pride ourselves of being super efficient. And this comes from really integrating all the different parts of Humio and building a lot of the things specifically for Humio. So if you're building a thing like this yourself, and I've had many colleagues who've tried building a do-it-yourself observability stack. You take some Kafka Spark for doing like real-time analytics and buffering. And then you need some Elastic and Hadoop-like thing to store the data and be able to search it. And if you build out a stack like this, of course you can get it exactly as you want it, but it's going to take a lot of time and it's going to be fairly complex. And you're going to get 3, 4, 5 different components that speak different languages. It's difficult to get consistency. And even though all the components are open source, none of these are ideally built for this particular use case. So we replaced many systems like do-it-yourself like this, just because of the complexity of operating 3, 4, 5 different databases and systems, etc. So Humio is kind of the same thing. It is this, it's a streaming engine and it's a data store built together that can deal with live data as it's arriving. So the streaming engine can look at data as it's coming in and trigger on this data on arrival. Then it stores it in a data store, and because most of the interesting action, all the stuff you do all the time, all the queries and actions you do all the time, they're happening in the streaming engine as data is arriving. The data store can be much simpler. It doesn't need to be optimized for the same use cases because it's really only used for incident response. It's not used for the day-to-day showing of dashboards, triggering off alerts, etc., which is where the bulk of the data is going. So this gives you one UI, one query language, and by kind of squeezing the implementation together, consistency and much reduced hardware. So kind of one of the things that probably triggers you when I'm saying this is this index-free data store there on the screen. And, it triggers a lot of people because how can you build a database without an index? That's kind of an oxymoron. So let's talk about that. So when you put data in an index, there is this basic trade-off that you do. Databases with indexes are fundamentally built with this trade-off where it really is a lot of work to put the data in, and that makes it really quickly to get the data out to search. That's kind of the point of indexing. So that also means that it's really built for low volume ingest and high volume query. Another aspect is this time-space trade-off where typically you'll see this, the indexes are actually much, much bigger, anywhere from 2 to 10x the data that you're putting in. Of course, that's a time-space trade-off, so you can stretch that. So the indexing that speeds up the querying is really what takes disk space, and it also takes a lot of CPU. So an index, if you take a step back, really is like this paper index you have in a library. When I was a kid, this was what an index would look like at the library. Right, so you need an index, and you need somewhere to store all the stuff that's indexed, all the books, right? They're on these shelves. But in reality, it really quickly becomes, the indexes take most of the space, and there's really only that much space left on your hard drives for storing the actual data. So with an index-free setup, the most naive would just be appending to files, and then because that's really, really quick. And then you need to spend more CPU to get the data out because you need to go search for it. So immediately you see the data because there's no index, you save a lot on disk space, and you can use that disk space to just store a lot extra data. So we easily get into replacement scenarios where we're letting users store 100x the data they could before on the same hardware. So given you have this kind of work, this mundane search work, so the right-hand side now is essentially sort of a grep. That's trivially parallelizable, so you can throw a lot of cores and machines at it. It's ideal for like a MapReduce style system or a shared resource system where whenever you run a query, you get an entire cluster for yourself for a short period of time. And then that's actually at the core what Humio does. That's how we get the interactive experience. When you throw lots of users at a large cluster, they don't all use it at the same time. So that's one thing. It's kind of at a high level, architectural level. If you dig in, we also put a lot of effort into streamlining and reducing I/O in the system. So if you imagine for a second that you have a 1 GB file you need to run grep on, or want to search what's in there. You run just a simple string search on a gigabyte of data. So first, in a typical setup, you would spend a second reading a gigabyte off the disk. That's typically a gigabyte a second for a modern SSD, and then maybe 100 milliseconds to search it. So of course we can do better than that. If you compress the data as you were beforehand, when it was arrived, you compress the data, you can reduce the reading quite significantly. So if you say it's compressed 10x, it would only take 100 milliseconds to read, then maybe half a second to decompress it, and then again 100 milliseconds to search it. So we're almost twice as fast already. Now this is trivially parallelizable. Of course, if you're on a 4-core machine, you want to do these 4 things in parallel. So if you imagine for a second, you take a quarter of this gigabyte of data, so that's 256 megabytes of data. And each of these cores decompresses that data. So compressed, it's maybe 25 megs. Decompressed is 256. Once you've done that, and you're running on one of these cores on a modern CPU, all that data that you decompressed, you loaded it onto the CPU core, decompressed it, and then because there's 256 megabytes of it, that's more data that can fit on those cores. So it's spilled out back out onto main memory. So actually, the pivotal trick in making streaming operations like this run really fast is to cut it into little bits and pieces, where each decompressed data unit is small enough that it actually fits on core. So you're saving an extra round trip to main memory, you're saving memory accesses up to main memory, and that makes it run like 10x faster, depending on what level of CPU caching you can get and the size of the data. So reading data in small chunks, decompressing it so that the decompressed data fits on the CPU is a super efficient way to run this sort of streaming operation. So it happens not in 4 little bytes like this diagram happens, but maybe in 1,000 bytes for each of these. So now, given that we have all this data compressed, in many cases you'll be able to have this compressed data already in your operating system's file system cache. So in most cases, there's actually no I/O wait to load the data. So putting together engineering things like this all the way through, you can actually make screamingly fast searches with something as simple as this. And that's because we don't have the indexes to carry around. The indexes load the data. They require random access across the file system, across the disks. So there's a lot of interesting scenarios where this actually pays off. So getting back to the data, we actually have sort of a metadata index, a small index where for each chunk of, we have these database files that are each a gigabyte. So we have an index over those, and we know, so when you run a query, you say, I want the last, notice in the demo before I said, first I searched the last 24 hours and I searched 30 days. So we have a time index that kind of can let you reduce the amount of the number of files that you need to look at. And we also have some Bloom filters that know something about the content that can optimize the query and reduce what you need to search for. So kind of really the core architecture is this. You have streaming query engine in front of this. So before the data is put into the data store, we allow streaming queries that can drive alerts and dashboards. And that's our own query engine. And then we have the data store that you would use for interactive ad hoc searches. So those two sides of the engine. In streaming, the streaming data, you can get materialized views. You process the data when it's in memory anyway, because it's kind of passing through. It just arrived. We're looking at it before we store it, so there's no I/O overhead there, and it gives really good response times for known queries. So when you have a dashboard, that would be computed in the streaming engine. And then the other use case you typically have is the incident response, digging in, trying to understand historic data. There we essentially just shift CPU load to query time. So all the stuff we saved for all the standing queries, all the queries you want all the time, we move it there. Use data compression, filtering instead of indexing, and then basically owning the stack the entire way down. So we're not using a third-party database. We have our own database. We're not using a third-party streaming engine. We have our own streaming engine, and kind of running that really smooth. Integrating all these parts is really what it takes. So I have some examples of use cases that I'm just going to show kind of from our own DevOps experience. I had more in the previous version of this, but I think there's a couple of things that might not be obvious. So one thing that has huge value for us is this, what we call the poor man's profiler in Humio land, and then something about putting metrics in logs. We'll get back to that. So in Humio, we generate these logs that are actually a thread dump that we push every 10 seconds. So every 10 seconds, we pause all of Humio, all the services, and make thread dumps of all the systems and dump it into Humio itself. So for instance, here could be a thread dump that's something inside Humio query coordinator or whatever. And you can see at the bottom there, what property we extract, the Humio line, is kind of the topmost stack element that actually has Humio in its name. It might be calling, later on, it might be calling into basic hash table or standard libraries or network IO or whatever. But the topmost query, the topmost stack frame that actually has Humio in its name, that's what we call the Humio line. And then you could take and say, I want all the stuff from operations cluster and show me the top Humio line. So this is how often does a given entry show up on in this. So it's very, very simple. Just a kind of the top stack entry that is related to Humio. What does that look like? Or we could show this over time. So this was you could show a time chart like this of Humio lines. So in a time chart, when you're showing that, you can disable the other so you can see some of these series are disabled. And actually here there was a bug in this case, in this multiplying running filter hasher with field.assign bits function that we run. And you can see late in the evening, I actually fixed that, and then the CPU load decreased quite significantly. So having these stack traces historically is super valuable also, because we can see if you're having a performance problem, we can compare that what does the stack trace, does the top stack traces look like today, and what do they look like yesterday? And actually just today we realized a new bug in the upcoming production release, release 17, that's coming hopefully any day, that where we were causing lots of SSH contexts to be created. So there's some code that would end up holding on to a lot of SSH contexts, and that could be a potential garbage collection or memory leak, for instance. And it showed up right away in a simple analytics on what had changed in terms of what are the top top log lines. So that was one trick. It's super simple. When you don't need a special profiler for this. This is just driving this kind of analytics out of a log file. Another thing that we do is all the metrics that Humio internally generate, we write them out just as log files. So here, for instance, is the event latency over various partitions of data. So this is the amount of time it takes from a log line to hit the front end of our ingest API and until it is available for processing for search. And it's been pushed through pushed all the way through the streaming engine. So all the live queries, all the standing queries that are there, they've been processed. And so this is by partition. These partitions are spread over some hosts. And so you see, typically, so we're very proud of this. The liveness of data in Humio is really on the order of a second, or that the mean definitely is typically below that. So this is driven off some data that looks like this. This is one log line, right? It says there's a metrics logger, and it says it's a histogram, that it's an event latency partition number 6. It has seen this many events, and then some median computations, etc. So you just take a log line just like this, and just draw it out with an expression like this, where you can see how we extract the partition number using a regex. Maybe you need to divide it by something and show it. So playing with your data in this way and putting your own data into your logs to be able to visualize it becomes the sort of super intuitive feedback loop for developers. If you're in a DevOps scenario, it's super easy to get production quality metrics out of your system, because you can just write something to your logs and you can immediately build something out of that that you can use to visualize how a new feature is being used, etc. So, yeah, I think I'll just end here. This was just the day I built this presentation. The day before, we actually had a production issue. So you can see, there was one of the nodes that got stuck, and you can see the delay was all of a sudden up to 3 or 4 minutes or something like that. Anyway, so I think I'll stop here, and then we have 1 minute for questions.